Hello and welcome to the 2025 Academic Decathlon in the subject of math. This is worksheet 1. There are lots of fun things for us to look at in here, but we'll start off with the warm-up problems. It says NRN, the real number system. So this is worksheet, prerequisite skills, simplifying radical expressions and exponential expressions. These are things that we should be very attuned to, rational or irrational. Rational radicals are perfect squares. So square roots that have a perfect square. So square root of 36 is a rational square root. And then we can have an irrational square root, which is the square root of 2, which cannot be simplified. If we look at that, if we type 36, take the square root, you see we get a rational number. If we take the square root of 2, we see we get an irrational number. Irrational numbers are non-repeating and non-terminating, meaning the numbers to the right of the decimal do not repeat and they never end. Even though it looks like it ends at 5 at the end of this calculator, it is just rounding that decimal. So, it says simplify the radical, so rad 32. That is not a perfect square, but it has factors within it that are perfect squares. 16 times 2 equals 32. And I can break that up because we can break up radicals being multiplied or divided. So I'm going to separate those into their own radicals. Square root of 16 is 4, and we get 4 rad 2, and that is irrational. So we simplified, and then we categorized it, labeled it as irrational. Why did I choose 16 and 2 opposed to 8 and no, 9 and 4, 2 and no, 3 no, 4. 4 is a perfect square, 5, 6. Well, it's a perfect square in there. I'll show you it later. The opposite of the square root of 25, the opposite of, that's kind of like -1 times the square root of 25. Square root of 25 is a perfect square, that equals 5. So -1 times 5 is 5, and that is considered rational. So that is a simplification. -2 cubed, notice that we have an exponent of 3 and a base of -2. The negative is included because we have Chewbacca. So we know that this is, yes, Chewie, we have -2 as the base, and we're going to multiply that base times itself 3 times. And that gives me -8, which is also rational. And then we have the square root of 3 to the 5th. Well, we could do it out. We could do 3 to the 5th, 3 times 3 times 3 times 3. But that's going to be a lot of, that's going to be a big number. Let's do this. We'll figure out 3 to the 5th power is 243. So yes, we can do the square root of 243, but that's very inefficient. We don't like making things bigger just to break them down. So what I would do is I would see that these two can be written as 3 squared. These two can be written as 3 squared, and then we have this leftover 3 in there. And I would separate each one of those into their own radicals, and we know that a square is going to cancel with the square root, so this produces a 3. A square is going to cancel with the square root, and then we're left with the square root of 3. These are outside, so we can do 3 times 3, which is 9 rad 3. Is it simplified, and that is irrational because square root of 3 is not a perfect square. So any non-perfect square radicals will be irrational. So number 4 is down here. Let's do number 4. Good. Okay. So now we're going to get into it, the real number system. And here we have radicals. Match each expression's exponential form to the radical form. So in here, these are all written in radical forms. You notice the radicals. These are all written with exponents, so that is called the exponential form. So now we have to match them. So how do we match those? And it looks like they want us to oh, that's very interesting. So they want us to, well, let's just take it. Instead of trying to fit, this is the square root of the cube root of 7. So I can rewrite this inside part. I'm going to rewrite this into exponent. So that would be written as 7 to the 1/4. And there's a 2 in there because it's invisible. So that, and then I would write this. I can take this radical, and that's to the 1/2. So I have 7 to the 1/4 to the 1/2, which equals 7 to the 1/8. And that would be 4. So we see, and that's much easier, opposed to, that's not sort of common eyeball. You don't look at that and all of a sudden see that that's 7 to the 1/8. But I don't know, you can, I'd much rather work it out. And let's do a little bit of work. So when we have the square root of 4, now let's do 3, that is 3, and there's a 1 here, and there's a 2 here. So that is to the 1/2. The exponent goes in the numerator, and the radical goes in the denominator. So if I get something like the third root of 5 to the 4th, that's going to equal 5 to the 4/3. This is radical form to exponent form, and we can go back and forth. So if I have 2 to the 2/3, well, that's going to equal, 2 is my base, the 2 squared, and then it's going to be the cube root because of the denominator. So we can also go from exponential form, exponent form, to radical form. Numerator is our power, denominator is our root. All right, let's look at B. So B, what are we going to do here? Oh, we're going to turn it. So here we go. This is a great example. Now we can go right to here. We can look at this one. This one is definitely an eyeball. That is to the 4/3 because the 4 is the exponent. That's going to go in the numerator, and the root is cubed, so that goes in the denominator. And we can also do it for C because that's easy converting. That's going to be x to the 3/4. And then, yes, we would understand. And how does that equal to the -1/2? That's kind of confusing. That is definitely a little bit more complex. So let's go into that component because it's a negative power. So when we have 7 to the -1, that equals 1/7. If we have 7 to the -2, that equals 1/7 to the 2nd. That negative exponent is representing items or bases in the denominator. So if I have 1/5 to the 3rd and I want to represent this base in the numerator, currently it's in the denominator. If I want to move it up to the numerator, I would change the sign of the exponent. So the exponent currently is positive, and if I move it to the, if I change its location, we're going to change its sign. So that's a nice, fun, not a lot of students know about that. If I have 1/3 to the -2, so it's currently in the denominator. If I move it to the numerator, I change the sign. So this one, it goes from negative to positive. Okay, so that's the little trick of that. And why is that? We can even go into a little bit more detail. If I have 7 squared over 7 cubed, we have 7 times 7 over 7 times 7 times 7. We have more in the denominator than the numerator, and these would cancel, and you're left with 1/7. So notice that we have the base is in the denominator. Well, remember that when we have like bases and we're dividing, we can subtract their exponents. So that would give us 7 to the negative 1, and that negative 1 just represents that extra base being in the denominator. Hopefully that makes sense. Let's go back to this one. So let's write it in exponential form first. So we have the fourth root of 7 over the square root of 7. So if we write that, that's 7 to the 1/4 over 7 to the 1/2. Okay, we have like bases, so let's subtract their exponents. And that gives us 7 to the negative 1/2. 1/4 minus 1/2 leaves us with a negative 1/2, which would be equal to, or that would be equal to 1 over 7 to the 1/2. Now, we don't like radicals in the denominator because that would be 1 over rad 7. And this, which we will find out, is a no-no. No, no. Also that, no, no. So that's why they put it in here. Yeah, that's a very interesting, tricky one. But those are your 4 problems. And super fun ones. No, I've already used that color. Let's use green. So D is equal to 2. Good. All right. Which expression or expressions below are equivalent to negative 3x to the 1/4 minus 2x to the 1/4 plus 6 times the 4th root of x? So, let's write them all in exponential form. So it's negative 3x to the 1/4 minus 2x to the 1/4 plus 6x to the 1/4. Now we have all like bases, or like terms. Like terms have the same base to the same exponent. So since these are like terms, we can combine their coefficients. So we're going to add their coefficients. Negative 3, negative 2, positive 6, which leaves me with positive 1. So that equals x to the 1/4. We wouldn't write 1. So you have x to the 1/4, which is in exponential notation. So this is okay. That's an answer. This is in radical form of x to the 1/4, not D. And then this is not 1 because that would be x to the 4th. So just B and C. Those are the 2 equivalent. No, no, that's x to the 4th. And this is negative x to the 1/4. So negative coefficient, that's a no-no. That doesn't have a coefficient of negative 1. This is a coefficient of 1. Number 3, simplify. All right, I'm going to convert this exponent, or this radical to exponent. And when we multiply like bases, we are going to add their exponents. So we're going to add the 2 exponents, and that is 5 to the 1/3 plus 5/3, which equals 5 to the 6/3, or 5 to the 2nd. Now that might be the answer, simplify, but I would just write 25. So I like that answer. What do they say? Yeah, 25. Yep. Good. Simplify. All right, first I'm going to simplify this exponent because that can be simplified. We have the square root of 81 to the 12 over 9. 12 over 9. 3 goes into that 4/3 times. Good. And so, all right. I'm going to, watch this, kids. I'm going to do this. I'm going to write 81 is 9 squared to the 4/3. And whenever we have a power of a power, do you know what we do with their exponents? We're going to multiply. So this becomes the square root of 9 to the 8/3. Okay, and then if we take this radical, so this is going to be 9 to the 8/3 times 1/2, because that's the square root part. This gets represented by this. And now we can cross cancel, because Mr. Mac loves to cross cancel before multiplying. Oh my goodness, we still get 9 to the 4/3. Hello, come on, extend that page. 9 to the 4/3, which can be simplified, which is the cube root of 9 to the 4th. And we're going to break 9 to the 4th into 9 to the 3rd times 9 to the 1st, because I want thirds, because I have cube roots. And this is going to give me 9 times the cube root of 9. So I separated each one, and I can't simplify the cube root of 9. Square root I could, but not the cube root. So that is simplified. It is irrational, but that's a really good question. Operate, whoa, operate. I love this word, operate. We have 12 to the 1/5 times 12 to the 3/5. We notice that we have like bases again. When we have like bases, in multiplying, we are going to add their exponents. So this equals 12 to the 1/5 plus 3/5, which gives us 12 to the 4/5. And then down in the denominator, those are not like bases. So we cannot add their exponents. So this is the 5th root. Yeah, that's going to be very interesting on what we do here. Okay, let's see. That's going to be really interesting. This is a good question because Mr. Mac is not familiar with it. I mean, the 5th root of, yes, I see what we're going to do. Got it. Because if we change this, this is the 5th root of 3 times the 5th root of 4. They have the same root, so we can put them underneath the same house, and that's 3 times 4, which equals 12 to the 5th root. Okay, so let's erase this. That becomes 12 to the 5th root. Hold on. That becomes 12 to the 5th root, which can be written as 12 to the 1/5. Now we have like bases, and we are dividing, so we're going to subtract their exponents. So this becomes 12 to the 4/5 minus 1/5, which is 12 to the 3/5. And I think we would just leave it like that. 12 to the 3/5. Yes, that's their answer. Yeah, I don't know, but probably 4, 3. You might be able to get rid of 4. Yeah, that could probably be simplified a little bit, but they like that answer, so that's good for us. Okay, operate and simplify. All right, this negative, so we can pull that out because you can't take the square root, but we know that the square root of -1 equals I. So we're going to write the cube root of 2 plus 2 times the cube root of -1 times 2. And we're going to separate those. Oh, cube root of -1. Hi, that doesn't equal I. That is the square root of I. Huh, okay. Okay, well, hold on. Here we go. Cube root of 2. So, okay. Yeah, cube root of -1 is doable. That equals -1. So we have the cube root cube root of 2 times, this is going to equal -1, because -1, cube root of, let's do this, cube root of -1. Well, we can write that as -1 times -1 times -1. And that would be written as the quantity of -1 cubed, which simplifies to -1. Haven't done that one in a while, so that was more than obvious. Cube root of 2, we're going to multiply these two because they're on the outside. Cube root of rad 2 minus 2 cube root of 2. Coefficient out here is 1. These are like radicals. Like radicals have the same radical inside and the same exponent, or same rad. So we're going to add their coefficients, which is 1 minus 2, which leaves me with negative cube root of 2. I wouldn't write -1, I would just write negative. That was kind of technical. All right, that's good. Equals I, but the cube root of -1 equals -1. That's something we should try to memorize and remember. Put that in our, what do we call, put it in our tool belt. All right, that was number, oh, that was just B. All right, so rad 6 and rad 30 can be rad 6 times rad 5. And rad 6 times rad 6, the 6 comes out, so that gives me 6 rad 5 minus, and this is 3 times 5 to the 1/2, which is the square root of 5, so that's -3 square root of 5. These are like terms. They're like terms because they have the same radical, and so we're going to combine their coefficients. We have 6 and -3, and that will give me 3 rad 5 as my answer. These are good ones. I like them. So much like terms, when you have 5x minus 3x, they're like terms. We combine their coefficients, 5 and -3, and you get 2, and then you just bring down the term, x. True or false? The zero exponent rule tells us that anything to the 0 power equals 0. So 5 to the 0 equals 1. Hello. 6 to the 0 equals 1. -10 to the 0 equals 1. The zero exponent rule tells us that anything to the power, 0 power equals 0. No, that is absolutely false. Almost everything to the 0. 0 to the 0 power is no solution. That's the only one to the 0 power that doesn't equal 1. Fill in the blanks using the words sometimes, always, or never. The product of a cube, the product of a perfect cube, so a perfect cube would be 27, the cube root of 27, and a perfect square would be 64, is always rational, because this is going to produce a rational number plus a rational number will always equal a rational number. That's good. That's always, we like that. Fill in the blanks, the quotient of a cube root of a perfect cube. Okay. No, that's 27. Let's do 27. The quotient of a cube root and the square root is rational. The quotient of a cube root of a perfect cube and the square root of a perfect square is rational? Yeah, that should be always. This is going to be a whole number. This is going to be a whole number. Any number over a whole number is always. It says sometimes, though. Why would it not? The quotient, that's the division of a cube root of a perfect cube. That's going to produce, and the square root of a perfect square, rational divided by a rational. Are there rationals that when divided by a rational, that doesn't make any sense? I think I know sometimes. All right, I think it's going to be sometimes. Do you want to know why it's sometimes? Because if we have the cube root of 27 over the square root of 0, that's going to equal 3 over 0, which is no solution. So that would make it irrational. That's the one situation. So it's sometimes. I guess that would be the one thing. That would be the only one that I'm thinking of. Fill in the blanks. A rational number plus an irrational number is always irrational. Doesn't matter what you add to an irrational number. Rad 2 is an irrational number. If we add rad 2 to it, that's irrational. 2, these you can't simplify that. That's what it is. So you still end up with an irrational number. You can't even add the whole number to the irrational number, technically. I mean, you can do the square root of 2, which equals that, plus 2 gives you this, but that's still irrational. So always irrational. No rational times, is always rational. Is never. I know what you were saying. It was always irrational. This is always irrational. AKA, but looking at what they were asking, sorry, I didn't pay attention. This is rational plus irrational equals irrational. The square root of a non-perfect cube is always irrational. Yeah, square root of a non-perfect cube is always going to be irrational. And it says sometimes. Oh, perfect cube, non-perfect cube. Mr. Mac, start reading the questions. Non-perfect cube. Well, hello. Yeah, sometimes. So square root of 1 is a perfect cube. So the square root, this is a perfect cube, but it produces a rational number. Non-perfect cube, sorry, non-perfect cube. That's a perfect cube, so that's not an example, sorry. So, of a non-perfect cube, 2, so the square root, this is a non-perfect cube, because the cube root of 2 is not perfect, and this produces irrational, okay? But we can give an example like 16, which is a non-perfect cube, but the square root of 16 gives us 4, which is rational. So sometimes irrational. It's irrational here, but not irrational, hence why it's sometimes. I'm sorry, I'll get better. Sorry about that. All right, so that is worksheet number 1. Let's look at some of the key things that are in here. This is the content portion of this, and it says the real number, just as exponents represent repeated multiplication by the same base value, radical signs denote repeated divisions by the same value. So this is called the index. I call it the root, but it's the index. This is called the radical sign, and this is called the radicand. So as we noticed, that x is to the power of 1, so that's where this 1 came from, and my index goes in the denominator. So this is the square root of 5 to the first, so the power goes in the numerator, the index goes in the denominator. And we see that we can simplify some radicals, and once we simplify them, we end up with like radicals. We can combine their coefficients. Like radicals combine their coefficients. These do not have like radicals, so we cannot combine their coefficients, and that is simplified completely. Here's some other stuff. When multiplying, oh yeah, this is good. So when multiplying, we multiply the coefficients. So multiplying, you're going to multiply the outsides with the outsides. Notice that 3 times 5, which is 15. And then we would multiply the insides with the insides. I absolutely would not do it in that manner. I would have tried to find like factors, like numbers. So, for example, let's do that. Rad 20 times rad 8. Rad 20 times rad 8. I'm going to break this into rad 4, rad 5. I'm going to break rad 8 into rad 4, rad 2. These are like radicals. It comes out. And these are the leftovers. So we get rad 10. So that would go out. And then if we had coefficients out in front of it, like we had in the other one, 3 and 5, so the 3 and the 5 go here, and the 3 and the 5 still are outside, and now we can multiply all of those to get 60 rad 10. So that's a good example. Yeah, 3 and 5. Oh, it's to the 4th root. Sorry. That was square root. We can do the 4th root, but, and let's do the 4th root. So I made a mistake there. The 4th root, let's make this to the 4th root of 20 and 5, and the 4th root of 8. So perfect fourths. So we know perfect squares is square root of 1, square root of 4, square root of 9, square root of 16, square root of 25, square root of 35, 36, and square root of 49, square root of 64, square root of 81, square root of 100. All right, those are perfect squares. Perfect cubes are going to be 1, 8, 27, 64, I think. 1, 2, 3, 4, 4 times 6, yeah, 64. I think that's 125. 5 to the 3rd, 125. 6 to the 3rd, 216. Okay, so I don't know. I don't know many past 125, as you could see. And then perfect fourths is going to be 1, is going to be 16, is going to be 81, is going to be 169? No, 196, I bet. 4 to the 4th. 4 to the 4th power gives me 256, not even close. 16 squared, yeah, 16 squared, 256, my bad. Whoa, we jumped real fast. For 256, holy moly. Well, we did go 11681. Okay, and that shows that going to the 4th power, and then what's that, 525? 5 to the 4th power, 525? 625. Okay, so when we go back here, yeah, I guess we should break it down, 4th. So, okay, yes, you should break it down. It's probably easier if we just break it down and then look for 1, 2, 3, 4. So a 2 will come out, and we'll be left with this, because this will be written as 2 to the 4th, and it'll come out and multiply the 15. That's why we get 20. Not bad. All right, let's look at the other stuff. When multiplying, we add. When multiplying, we add. Now, we can't add without like denominators, so we would convert the denominators and then add the numerators. When raising a power of a power, we multiply 1/2 times 4. Yeah, this is rationalizing. So we have to rationalize radicals. I told you earlier that you can't have radicals in the denominator. So if I have 1 over rad 2, you can't leave that as your answer. This is what we call unsimplified. It's not simplified, but it's not rational. It's irrational. So how do you rationalize it? Well, what would get rid of a rad 2 is another rad 2. And if we want to keep it equivalent, I have to make this a value of 1. Since it's equivalent, this has to be a value of 1. So this gives me rad 2 over 2, because any radical times itself comes out. And that is it. You can't simplify the 2's because the denominator is outside the radical and the one in the numerator is inside the radical. So that's one example. You can have 3 over rad 5. So to rationalize it, let's do 6, yes. Let's do 6, that's way better. So to rationalize it, you multiply it by rad 6 over rad 6. This becomes 3 rad 6. You can't combine those. That's outside, this is inside. Those are unlike. You can't multiply. And then rad 6 times rad 6 is 6. Now, we look at the coefficients. The 3 and the 6 are outside, so we can simplify that. And that simplifies to 6 over 2, or rad 6 over 2. So that's a good example of rationalizing, and then you typically have to simplify. That's rationalizing. When we divide, we subtract. 0 exponent rule, negative exponents go to the denominator. Multiply like bases, you add their exponents. Divide like bases, you subtract their exponents. Power of a power, you are going to multiply those exponents. All right, that's it. Good job. Have fun. Good luck. Let me know if you have questions.